This talk is about providing tenants or users in shared data centers absolute throughput guarantees that hold across all of the resources that they use. Currently, tenants are moving away from enterprise data centers, where they have access to dedicated infrastructure, to large cloud data centers, where they share these resources with other tenants. And the primary benefits of doing this are cost savings and also elasticity. However, there's another major benefit, which is easy access to services like persistent storage and middleboxes. In particular, these services are implemented via appliances, such as key value stores and load balancers. And while these services are great because they're fully managed and they can scale on demand, they suffer from a major drawback, which is that the underlying appliances that implement these services are shared among many tenants. And to see why this is a problem, let me give you a really quick example. I'm depicting 3 tenants that are using a traffic optimizer appliance that performs compression on tenants' requests. And when all 3 tenants are lightly using this appliance, all of them enjoy good performance that satisfies their needs. However, when the GitHub tenant starts increasing its demand and starts sending many concurrent requests that add to the appliance, and we call this process being aggressive, what happens is this tenant starts consuming the majority of the resources. And this affects the quality of service that other tenants receive. Indeed, recent measurements of cloud data centers show that the throughput achieved by a tenant at appliances and network resources can vary by as much as a factor of 5. And the implication of this is that applications experience degraded and unpredictable performance. Existing systems provide guarantees to tenants across network resources or across shared appliances. However, tenants in data centers today use both types of resources simultaneously, and combining these systems does not ensure end-to-end guarantees. What I mean by end-to-end guarantees is guarantees that hold regardless of the bottleneck resource. And I'm going to illustrate the difference with a very simple example. If you consider 2 tenants that are accessing a storage server via the data center network, and we have the GitHub tenant that's issuing read requests, that when they travel on the network to the storage server, they're very small because they're only the request header, so maybe 80 bytes. On the other hand, we have the Reddit tenant that is issuing write requests that they're very big on the network because they contain the actual payload. If we try to isolate this request using network semantics, which usually comes down to request size, what we end up having is more reads reaching the appliance than writes. And this is because mechanisms that perform network isolation do not really understand appliance semantics, and they do not know that read requests can be just as expensive as write requests. If we isolate this request at the appliance, what we find is that this doesn't really help because read requests are disproportionately more prevalent and crowd out the write requests. And sort of the key takeaway here is that we need a new abstraction to capture semantics of guarantees that hold irrespective of the bottleneck resource. And towards meeting that goal, I'm going to first present the virtual data center abstraction, which we use to encapsulate end-to-end guarantees in a way that's easily understood by tenants and the provider. At a high level, virtual data centers abstract away the details of the provider's physical infrastructure and give tenants their own view of a simplified data center topology that closely resembles an enterprise data center. Virtual data centers are composed of virtual machines that are connected through a virtual network to other virtual machines and virtual appliances. Each link connecting a VM and also each virtual appliance is associated with a guaranteed virtual capacity. And these virtual capacities can be fixed or they can be minimum. And this ensures that we can satisfy tenants who desire predictability, so they don't want to have more resources given to them than what they want. And also tenants who want a minimum level of service and who also want the benefit of the elasticity provided by cloud data centers. I want to make one thing clear before moving forward, though, and that is that if the provider wants to provide guaranteed throughput to tenants, it needs to provision the data center in such a way that it can actually meet those guarantees. So in the paper, we describe a placement and an admission control protocol that we use to place tenants' VDCs so their guarantees can always be met. Now that I've explained the high-level idea of the VDC abstraction, let me discuss the throughput metric that we use to specify the guaranteed virtual capacities. But first, I'm going to highlight the trade-offs of existing metrics and why we chose not to use them. On the one hand, we have relative metrics like percentage share of the appliance. And these metrics are great for the provider because they're very easy to provision for, but they don't really fit well with the virtual data center abstraction because they're meaningless to tenants and performance remains variable. On the other hand, we have metrics like requests per second, which are great because they're absolute, so tenants know what they're getting. But they suffer from the issue that they require the provider to provision based on the costliest request. And the reason behind this is that the cost of different requests varies with request characteristics. So for example, if we look at a SSD-backed block store, we notice that large write requests are much more expensive to serve than small reads. And as a result, the capacity of the appliance varies with the workload, which forces the provider to provision for the worst case scenario, in this case for these large writes. And this turns out to be very conservative. So to make offering guaranteed throughput palatable to the provider, we came up with a throughput metric that remains absolute, but that gives more flexibility to the provider when provisioning resources. And we call our metric virtual request cost, and the units of this metric are tokens. And for each resource, the provider is going to specify and advertise a virtual cost function that is going to map observable request characteristics, for example, request type, request size, and so on, to their cost in tokens. And these functions are going to be derived through benchmarking or domain expertise, but crucially, these cost functions do not need to be perfect. And later in the talk, I'm going to describe mechanisms that we use to mask the imperfections of these cost functions. Using virtual request cost as a throughput metric means that we can specify all guaranteed virtual capacities in a unified cost model. And in this way, we don't have to worry about quantifying network throughput in bits per second and then storage throughput in IOPS and so on. Furthermore, virtual request cost strikes a good compromise between tenants and the provider. Since cost functions are fixed, tenants obtain absolute throughput guarantees that they can map onto other metrics. For example, given this key value store, this cost function for a key value store, and a guarantee of 32 kilotokens per second, a tenant with a workload consisting primarily of 8 kilobyte puts can determine that it can receive, independently can determine that it can receive 2 puts per second. And similarly for a tenant issuing 32 kilobyte gets. Lastly, virtual request cost adds a level of indirection that allows the provider to provision less conservatively. And what this means is that we can pack more tenants' VDCs onto the physical infrastructure. Now that I have described the VDC abstraction and the metric that we use for guaranteed virtual capacities, let me discuss how Pulsar manages resources after tenants have been placed. But first, let me start by describing our design goals, which will explain a lot of our design process. Our first goal concerns ease of deployment. We wanted our system to work without having to modify any appliances, switches, guest OSes, or applications. And since providing the VDC abstraction, in a sense, requires rate limiting tenants who are aggressive and who try to use more resources than their guaranteed virtual capacities, we ended up adding this functionality directly to end hosts via a hypervisor module that we call the rate enforcer. Our second goal concerns utilization, or resource utilization. Since we want to give tenants who have minimum guarantees more resources when they need them, we need to have a mechanism to claim those resources from tenants who are not using them. And the implication of this is that we need a mechanism to coordinate the rate enforcers. Lastly, we want this rate enforcer coordination to be done in accordance to rich policies, and we want these rich policies to be very simple to implement and also very simple to change. So our design decision is to implement this logic in a centralized controller. And this is very reminiscent of some of the papers that we saw this morning, where we decouple the data and the control plane, and in our case, we do so to provide throughput guarantees. Now, recall that to avoid appliance modifications, we add a module to the hypervisor called the rate enforcer. This rate enforcer performs 3 critical tasks. First, it estimates VM demands. By that, I mean the demand that the VM has for each appliance and network link. And then the rate enforcers emulate the cost of serving a request at all resources by applying the cost functions that were advertised by the provider. And this allows the rate enforcers to ensure that VMs do not consume more resources than they're allocated. Pulsar also introduces a centralized controller that has visibility of tenants' VDCs and the physical topology of the data center. And the controller computes allocations for each VM that are used to coordinate the rate enforcers. And the controller also estimates the capacity of appliances, since these capacities can vary and we need them for rate allocation. Finally, the controller communicates with rate enforcers in control intervals to exchange information about VM demands and VM allocations. Now, in this talk, I'm going to focus primarily on what the controller does. And I'm going to start by talking about RAID allocation. The goal of RAID allocation is for the controller to decide how much resources each VM can consume. And the idea is that if VMs collectively follow these allocations, the data center will neither be underutilized nor will tenants' guarantees be violated. And the inputs to RAID allocation are the capacity of each resource, which is estimated by the controller, every control interval, and also the demands of each VM, which are estimated by RAID enforcers. The output of the allocation mechanism is a vector for each VM to VM pair, where each entry contains the amount of tokens that the source VM can consume on each resource in its path. Now, recall that these allocations are used to coordinate RAID enforcers, and one of our design goals was that we wanted to be able to coordinate this coordination via rich policies. I'm not going to go into the mechanisms of how we perform RAID allocation, but I do want to talk about the kinds of policies that we can enable. Allocations are based on two types of policies. The first type are policies specified by tenants that describe how the guaranteed virtual capacities are to be distributed to tenants' VMs. And the reason that we need this is that if you look at the VDC abstraction, it defines what the guaranteed virtual capacities are, but it says nothing about how they are to be distributed to the underlying VMs of each tenant. And so this is the purpose of this tenant-specified policy. So types of policies that we can handle are, one sensible default will be to just share the virtual capacity fairly across all VMs. But Pulsar can actually do better than this. It can actually enforce cool policies like give all the resources fairly to all VMs, unless the third VM is active, in which case give all the resources to that VM because it might be running a critical task. The second type of policy is a provider-specified policy that defines how spare resources are allocated to tenants with minimum guarantees. And again, a sample policy can be distributing resources fairly, but the provider can also choose to not provide any fairness or efficiency and focus on a different metric like maximizing profit. Now recall that one of the inputs to RAID allocation is the capacity of each resource. However, as I've explained in the talk, appliance capacity varies based on the workload, and so we need to estimate it dynamically. The way we approach this problem is by first recognizing that congestion control protocols implicitly estimate network capacity, so they get us most of the work there. And the basic idea of these protocols is that each independent network flow continuously probes for a higher capacity until it detects congestion. And while we apply this general principle to our mechanism, we do not directly use existing protocols because they pose some challenges. So first, congestion signals like packet loss are not universally supported. And signals like latency are very noisy, especially if VMs are accessing an appliance for widely different paths. Second is that these protocols are typically distributed, which is great for scalability, but it introduces complexity and hurts convergence time. And also because of their distributed nature, capacity estimation and resource allocation are tightly coupled, since flows independently allocate resources to themselves. However, if you think about the RAID allocation process of Pulsar, we need to allocate resources in accordance to tenant-level semantics and high-level policies. So we need to decouple capacity estimation from RAID allocation. So what we do instead is we leverage the global visibility and centralization of our controller to develop a simple capacity estimation mechanism. And the high-level idea of this mechanism is to maintain a window where the capacity estimate is expected to lie, and then refine this window based on the presence or absence of congestion signals. And mechanistically, what this comes down to is we start the estimation process by effectively doing a binary search in this window. And then if we detect congestion, we revert to a previous estimate, and we let requests go through. And then we repeat this process by, and in the meantime, refining this window. And eventually, when the window is small enough, we have a control equation that reacts to the small fluctuations in the workload. And if the workload changes significantly, the estimation process is restarted. And we rely on two congestion signals that are useful in our context. The first one is that if the throughput that we achieve at an appliance is much lower than our capacity estimate, this serves as a very strong signal that the appliance cannot keep up with its workload, so the estimate is probably too high. The second signal is actually needed because our goal is not really to find the maximum appliance capacity, but rather the maximum appliance capacity that corresponds to a workload where all guarantees are met. And these two are different because capacity depends on the workload. And so to disambiguate between these two cases, we need this signal. And you can find more in-depth description and an example in the paper. Now I'm going to go into the implementation of Pulsar. We implemented the rate enforcer in Hyper-V, which is the hypervisor that we use. And the enforcer enforces the allocation provided by the controller using a new multi-resource token bucket that we developed. And our controller is going to run on a separate server. And we implemented the allocation policies that we're interested in using multiple existing multi-resource allocation mechanisms, including DRF and HDRF. I want to answer 3 evaluation questions. And I'm going to go and, OK. I'm going to answer 3 evaluation questions. And the first one is, can Pulsar actually isolate tenants? The second one is, can Pulsar estimate appliance capacity? And finally, I want to talk about the data and control plane overheads that Pulsar introduces. And I'm going to answer these questions in the context of our evaluation setup. So our testbed consists of 3 appliances, an in-memory key value store, a block store that's backed by 6 SSDs, and an encryption device that performs RC4 and AES encryption, and it's implemented in the hypervisor of each compute server. Our network is a 40 gigabit per second network that connects 10 compute servers, and we have a total of 113 VMs running on these servers. We have 4 tenants, A through D, and most importantly, all of these tenants are going to share at least one resource. And each of these tenants will be driven by a workload that is generated from parameters derived from hot mail traces. And you can find a description of these traces in our paper as well. We have derived virtual data centers for each of these tenants. But for simplicity, I'm just going to tabulate the throughput that each tenant should receive or should achieve, given the setup that we have and also the workloads of the tenants. With a star or an asterisk, I have labeled the tenants who are aggressive, meaning they're going to try their best to get the most resources out of the data center by either having many network flows or by having long I/O windows. So when we run this workloads without Pulsar, what we observe is that tenants who are aggressive achieve the majority of the throughput. And this is to be expected since we're not performing any kind of rate enforcement. And as you can see, tenant B and D miss their guarantees by 64% and 32% each. And again, this is because the baseline system has no notion of guarantees. On the other hand, when we actually turn on Pulsar, what we see is that we are able to meet all tenants' guarantees. Furthermore, in this experiment, the controller distributes spare resources in proportion to tenants' guarantees, which is why tenant B achieves a much higher throughput because he has the highest guarantee. Now, you may notice that the overall throughput on the Pulsar is about 7 to 10% lower than the baseline. And this is because by enforcing guarantees, Pulsar is effectively changing the nature of the workload that's being serviced by the data center. And depending on what the workload is and what the cost functions are, and also, the total throughput on the Pulsar can either be higher or lower than the baseline. Now I want to talk about whether or not Pulsar can estimate appliance capacity. And in this experiment, we have 3 tenants that all share an in-memory key value store. And each tenant has a different workload. And the capacity estimate is depicted as a black line that you can see at the top. And the shaded colors represent the throughput that is achieved by each tenant. So initially, we run a single tenant and let it use the appliance in isolation. So our capacity estimate starts low and quickly ramps up to the appliance capacity that satisfies that tenant. And then we start a new tenant, and this effectively causes the workload that is received by the appliance to change. And what happens is Pulsar detects this workload change and comes up with a new capacity estimate. Finally, we repeat this process, and we observe similar results. And in all these cases, the capacity estimate converges in less than 10 seconds, or 10 control intervals. Now I want to talk about the data and control plane overheads. So because the enforcer is implemented in software, this introduces 2% overhead for most types of requests and 15% overhead for very small requests, like 512 byte requests. And this is due to data structure locking at 40 gigabits per second speeds. As far as the control plane overhead, the biggest issue that we have is that some of the allocation policies that we're trying to implement are very compute heavy. So for these rich policies, we can handle about 24,000 VMs and 200 appliances. But for less expressive policies, we can handle many more. And you can look at the paper for details. So to summarize, I presented the virtual data center abstraction, which captures end-to-end throughput guarantees. And then I present the Pulsar, which implements this or gives this abstraction to tenants. And crucially, Pulsar does not require any modifications to appliances, switches, guest OSes, or applications. And with that, I conclude my talk, and I'm happy to take any questions.
Chris Koziraki, Stanford. Very interesting talk. I want to understand a couple of things a little bit better. First of all, how often does the application need to reevaluate the relationship between tokens and performers? So if my application changes over time and maybe the hardware that I actually use changes, what does this mean for me in terms of knowing that write request is 2 tokens and read request is half a token?
So in our implementation, or really in our design, cost functions are fixed. So when a tenant comes into the data center and says, hey, provider, I want to have my own private virtual data center, the tenant will specify the guarantees in tokens per second, and the provider will have pre-advertised cost functions for each resource. So this mapping will not change. In principle, you can imagine changing cost functions over time, sort of to improve your measurement. But if cost functions are fixed, then as far as the tenant is concerned, you do not have to worry about tokens meaning something other than what you expect to begin with.
And then if I may also ask a second question, what about latency? So obviously if you have a queuing problem, then throughput dominates. But have you done an experience with low latency services and see if there are any issues that you have to deal with there?
So we do not provide latency guarantees, but I do not, in our experiments, we have not noticed any issues with latency problems.
Thanks.
Yeah, sure.
Yeah, thanks. Nadir from University of British Columbia. Your answer cleared my first part of the question, which is fixed cost model for the tokens. But I wonder if it was dynamic, how Pulsar will handle the overhead, like control. You said the overhead is not high, but I assume if token price is changing, how would it affect your overhead for handling requests?
So you mean the rate enforcers? So the rate enforcers, effectively the way they're implemented, for each request that comes in, they sort of price request by applying the cost functions. So if your cost functions are very complex and they take a lot of CPU time, then I can imagine rate enforcers being CPU heavy. However, our design principle has been to keep the cost functions fixed and instead deal with the inaccuracy that these cost functions might impose by estimating the capacity of the appliance. So there's a very tight coupling between cost functions and appliance capacity. So if the cost functions are perfect, your appliance capacity will not vary at all. So that's kind of cool. But if your cost functions are really bad, your appliance capacity will vary quite a lot. So that's why we chose to keep cost functions fixed and deal with that.
Okay, thanks.
Push that, yeah.
Hi, Tim Wood from George Washington University. I think we all have similar questions about the cost function. So to me, it seems like the really difficult part of this is mapping application performance to these tokens. So how do you go about doing that? Because otherwise, it doesn't really help me to have a guarantee about tokens.
That's an excellent question. And so, in fact, the premise of many recent works has been, I'm a tenant, I have an application, I have no idea what guarantees I need. And so papers like Cicada and Bazaar, sort of the high-level contribution of these papers is they take high-level requirements such as job completion time, and they map it into the guarantees that you would like to have. And so you can imagine using these systems to derive the guarantees for the Pulsar can enforce.
Hi, my name is Henry from Stanford University. Can you go back to the graph where you showed the new applications coming up?
The graph when I showed the new application. Oh,
this was 1 to 2 and then up to 3.
This one?
Yeah.
Okay.
So we noticed there's a dip during the estimation phase. Is that because it's being very conservative during the estimation phase?
Yeah, so every time we notice a high workload change, what we do is we restart the process from scratch. And so we're very conservative about where we start the process because we don't really know where this estimation is going, where the capacity is going to lie. So we start low, and then through the binary search phase, we sort of converge quickly.
Have you considered what would happen if you had a lot of short-lived applications that are perhaps live shorter than your estimation time?
So the estimation time is configurable. I presume that if the workloads that your data center are servicing happen in very short timeframes, you can adjust the control interval to adapt to those short timeframes.
Thank you.
Yes. Okay. Thank you.